My name is Rafael Ponte, and I will talk about distributed scheduling with Spring Boot. Thank you so much for your time. This is my first time here in Barcelona and in Spring Boot as attending and also as a speaker. So I'm just trying not to freak out. Please. So be kind to me, okay? As I said, my name is Rafael Ponte, and I will talk how we can design and implement a resilient and scalable background job with Java in Spring Boot. I like to think about this talk as if I had a senior software engineer doing a code review of my code. How he or she will look at the context, detect some red flags in the code, and reason about each one of them. And of course, how he or she solves those issues. When I talk about background jobs, I have a true belief that almost everything in software can be solved with a job running every 1 minute. I mean, we can have a background job just to clean up our old files from the disk, or to send emails to lazy users, to keep systems up to date, or even to fix data in the database. If you think further, you'll realize that a background job exists everywhere, such as your operational system like Windows, Linux, or your Kubernetes. But implement a background job sometimes can be harder. Design and implement a background job can be harder than you think. I mean, depending on your context, your system and business requirements, building a background job might become a nightmare of bugs and workarounds. This does not happen for nothing. Usually, implement a background job involves implement multi-threading code. In these scenarios, we have to deal with threads, mutex, semaphores, locking, and race conditions. And probably you know that concurrence and parallelism are not easy things at all. Besides multi-threading, the chances are that we'll have to deal with distributed systems. It's impossible to talk about distributed system without mentioning the 8 fallacies of distributed computing. Those 8 lies try to hide from us how hard it is to build a distributed system. The only certainty that you have is that the network will fail sooner or later. And when you combine concurrent and distributed computing, you find the worst scenario and environment to design and build distributed background jobs. If you don't have solid fundamentals in the subjects, you are probably in trouble. So, to understand how this can be hard, we need a context. So, our context will be a simple fintech use case, allowing a customer to request a new credit card. To get this new credit card, the customer needs to fill out a proposal, a simple form in the mobile app, and submit it, so that the fintech company can evaluate his proposal and verify if this customer is eligible for a credit card. If so, he will receive a new credit card at home. In order to implement this solution, we can have a microservice that exposes a REST API to the mobile app. Something like that, a simple back-end architecture, so that the customer can submit his proposal, and the back-end can process and save it in the database, and also send a copy of this proposal to another microservice responsible for evaluating in detail, like fraud analysis and credit limit. If everything is okay, the credit card will be produced and sent to the customer. However, it may take some time. the user needs to be notified about the progress of his credit card. In order to notify the user, the same application can have a background job responsible for checking the progress of the credit card. Therefore, getting the credit card progress and updating the proposal in the database for all users. So to implement the solution, we will use the good old Java, Spring Boot and its schedule module. And not least, a Postgre is our database. But before we get into our solution, let's remember how to schedule a task with Spring Boot. First, we need a simple Java class with any name and a method without argument and with no return. I mean, a void return. This method will run our business logic. This is a simple Java class. Spring doesn't know anything about it, so we need to make Spring aware of it. To do that, we must annotate the class with the component annotation. We also need to indicate to Spring which method to run our task. So we annotate the method with scheduled annotation. Finally, using the fixed delay attribute, we set this task to run every 1 minute, or 6,000 milliseconds. That's it. Simple, right? Now, let's come back to our fintech context and solution. On this solution, we will only implement this part, a background job with Java and Spring Boot. Here is the code of our solution. Don't worry, let's walk through it. We have a class called attach card proposal job, a meaningful name, with a method called execute. Our business logic is not that hard. The first line fetches all the eligible proposals for the database, the pending proposals, and iterates over each one of them. Execute this business logic here. For each proposal, we verify its progress on the microservice or an external system. We convert that response DTO into a domain model, into a card entity. And we save this card in the database. After, we attach this card to the current proposal and change the proposal status. Finally, we update the proposal in the database. Of course, we also schedule this method to run every 1 minute via scheduled annotation. Nothing complicated, right? Probably you have already done something similar to that, like a job sending emails, for example. This code is okay. It works on my machine, and probably it works in production. But depending on the context, system, and business requirements, this code may be full of red flags. Maybe a junior software engineer cannot see any one of them, but a more experienced and senior developer doing a code review can. And again, depends on the context. If you don't fix many of them, we can have severe problems in production. That's why I usually call this code a naive solution. And if you want to see and fix some of these red flags, please stick to me. My name is Rafael Ponte. I am a Brazilian software developer at Zup. I have been working with Java and distributed systems for more than 19 years. And I love to work with boring techs like Java, Spring, Hibernate, SQL, and relational database. That's why, in Brazil, I'm also known as the Maharaja of the Legacy, and sometimes the Prince of the Ocean. So, now it's time to see what are those challenges and pitfalls when implement our background job with Spring Boot. Let's get to our naive solution. From now on, we will focus on this code. So let's walk through our business logic again. First, the code fetches all the eligible proposals from the database. To do that, the Spring Data repository generates this SQL query for us. Sorry, my throat is terrible. A simple select. Now, for each proposal, get the credit card progress from the external system, saves the credit card in the database, and also update the proposal status. That works, but what if the application crashes? What if the application is restarted? What if the machine is recycled by your cloud provider? How does this code behave in such situations? Let's focus only on this method. We have a few I/O operations here, but two of them are write operation. They change some state in the database. The first operation inserts a new card in the database. The second one updates the current proposal with its card. That's why we have an insert in the table card, and we have an update on proposal table. The problem with this code is that those two operations, write operation, are independent from each other. Both begin and commit their own transaction. That's similar to run our application without commit enabled. Which means that if you have a crash before or after the loop, you are okay. But as soon as you have a crash in the middle of this write operations, right between them, we have a bug of data inconsistency. It means that on the database side, the business logic will insert the new credit card. However, due to the crash, the business logic will not be able to update the proposal. And as you can see here, there is no reference to the inserted credit card. A question that we should make to ourselves is, how will this application behave in the presence of crash or restarts? Maybe it works, maybe it doesn't. But maybe you remember my actual belief that almost everything can be fixed with a job running every 1 minute. At this moment, we have a background job running every 1 minute to process the proposals. But sometimes, when a crash happens, it can get some data corruption errors. And maybe a clever solution could be create a new background job that runs every 5 minutes to detect and fix those corruption rows. Right? Does it make sense? Yes, of course. But no, we will not use it. I mean, although we will not implement this solution on this talk, don't be fooled. This kind of solution is very common in the enterprise industry. So, how can we fix that? If you have worked enough time with relational database, you probably know that we need a transactional wrapping this business logic, so that these two write operations will be treated as a single atomic operation. It's all or nothing. That works because the transaction follows the ACID properties of our relational database. So, in order to do that with Spring, to have a transaction, we just need to annotate the method with @transactional annotation. So now, in case of crash or restarts, our application and database will keep our data consistent. Yes, that's amazing. We just got recoverability. We not only fix the bug in case of restart and crash, but we also obtain the ability to prevent data corruption so that the application can return to running safely. But what if the data volume grows? What if our job stops working for 1 hour, 1 day, 1 week? It doesn't matter the reason. What if the fintech company aggressively campaigns to get new customers? How does our code behave in such scenarios? Let's understand that. If the data volumes grow more than expected, this single line of code will crash our application. This is a red flag. It will run this SQL query, responsible for fetch all the eligible proposals from the database. When this happens, our application memory footprint will get higher, 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 until an out-of-memory error happens. And when the out-of-memory error happens, your operational system will detect it and kill your JVM process. Our job is dead. To understand why that happened, we need to know how this method works under the hood. For that, we need to look at the proposal repository. Here, we have a simple Java interface that extends the JPA repository interface from Spring Boot. Since you are using the Spring Data JPA repositories, we know that that method name conventions matter. I mean, Spring Data uses the method's name to generate the SQL statements at runtime. If you look at the method name, we can see this find all prefix. It indicates that Spring Data should load all the entries from the table with this SQL. A select without any limit in the number of rows. And when you don't have any idea how many rows your table has or how fast this table might grow, we should never write a select like this one. A select that finds all the entries from the data table, from a table. We don't need all this row. We only need a small amount of them. I mean, instead of fetch all the rows, we could fetch only the top 5, top 10, the top 50 rows from the database. This number depends on the context. So, after fixing the method name, our select changed from this to this. Select limit 50, our top 50 proposals. This is our fixed code. But this loop will end very early. That's not what I wanted. Yet this loop will only execute on the next execution. What I want is to process all the proposals from the database, but in chunks of records at a time. For that, I need an infinite loop, a while true block. So this is our simplified business logic. And now we put it inside a while true loop. We also need a condition to verify when there is no more proposal to process. And of course, exiting from the infinite loop. But after running this code, we still get the same out-of-memory error. What did I do wrong? Let's review the code one more time. We have this infinite loop. We are fetching only 50 objects at a time. We are also creating new local reference inside the method scope. There is no reference outside this method. We also are exiting the loop at the right time. So why? Why this is happening? This is happening because of this annotation, transactional annotation that we put few steps ago. To understand why this is happening, we need to know which persistence framework the application is using. Looking at the repository, it's clear we are using the Spring Data alongside JPA and Hibernate. That's important to know because the Spring Transactional Management may work differently depending on your persistent framework. That's why we need to revisit JPA and Hibernate. Therefore, let's review the job's workflow as we expected to happen. Here, we have our job in the database. When the job is triggered, the Spring Scheduler calls the repository. That calls the JPA's entity manager. that generate the SQL and send it to the database. Then the database responds the entity manager with a chunk of records, which in turn pass the chunk of entities of objects to the repository that finally pass it to our job. And then after process this chunk of entities, objects, those objects should be discarded and collected by JVM garbage collector. And this is a loop. And this inside a loop, an infinite loop should work the same way. That's what we expected. But actually, this is not what we have got. What we have got is a long-running transaction. To understand what that means, let's get back to our workflow. Since you are using each transactional annotation, our job workflow is inside a transactional scope managed by the Spring Boot. So that chunk of object should be collected by the garbage collector, but it isn't, because there is a reference to it in the entity manager. That happens because the entity manager also works as an in-memory cache. That's why the entity manager is also known as the JPA first level cache. And inside this loop, NDAPs accumulate all the entities that were loaded from the database into the application memory. The idea, the insight here, is to understand that this transactional annotation, which is managed by Spring Boot, has a close relationship with JPA Entity Manager. There is a high level of intimacy between them here. They are very, very close. That's why when a transaction is destroyed, its entity manager is also destroyed. In other words, if there is no transactional scope, there is no entity manager or in-memory cache. Now it makes a lot of sense. So you think, I just need to remove the transactional annotation here. And that's it. There is no more long-run transactions. Since there is no transactional scope, the entity manager will be created and destroyed at each repository method call. It's too short life for an in-memory cache. But we still have those two write operations here. And without a transactional scope, we are giving up on the data consistency. No, we don't want to do that. We learned a few steps ago that this is a dangerous approach. So how can we avoid long-running transaction without giving up on the data consistency? The answer is we need a short-run transaction. To understand what is a short-run transaction, let's look at the job's life cycle. The job starts here and ends here. Imagine this job takes 1 hour to conclude the job execution. Now, what we have is a single transaction that lasts as long as the job execution. It starts here and ends there. We call it a long-running transaction. A long-running transaction is very bad for the application and mainly for the database as well. We need to minimize it. So, to achieve that, we need a small transaction that lives less than the job execution. I mean, a transaction that starts here and ends there, for example. That's what I call a short-run transaction. However, a single short-run transaction is not enough to process all the proposals from the database. That's why you need not only one, but 2, 3, 4, or as many short-run transactions as possible, so that our job can process all the proposals in the database. Now, the job's workflow will be different because you are using short-run transaction. Because you have this short-run transaction here. So when the job is triggered by the Spring scheduler, it will accumulate only a few objects in memory. And when the transaction is destroyed, the entity manager will also be destroyed. If there is no transaction, there is no entity manager. If there is no entity manager, there is no first level cache and no objects in the memory. So those objects can now be collected by the JVM garbage collector. And this will keep working in a loop until all the proposals are processed by the job. But to implement short-run transactions, we need to have a precise control of the transactional scope. For good or for bad, we need to use a different approach with Spring Boot. We must stop using a declarative approach, like annotation, and start to use a programmatic one, the programmatic transactional management. Here is our simplified code. It would be very, very nice if you could move this annotation into the method body inside the while true loop, like this line here. And this annotation could have an executed method that receives a lambda block to execute a business logic. But unfortunately, an annotation does not execute anything. It's just a metadata. So instead, we need the same component that is responsible for evaluating this annotation and manage the transactional scope. We need a transactional manager. And to use a transactional manager in our code, we need to inject a transaction template. After refactoring, this is our code use the transaction template to handle short-running transaction in the loop, inside the loop. Now, when the job is triggered again, this is going to be our new application memory footprint. It will be under control. There is no more out of memory. Congratulations, we just got batch processing. We not only avoid the out of memory error, we are now applying a batch processing via short-running transaction. This is the right way to implement batch processing. But, as the life is not easy, what if? What if we run the application in cluster? What if we run our background process not in one, but in two or more machines? What if you need high availability for our solution? I mean, what I want to say is that today we have a single machine running our Spring Boot application. And we have a proposal table in the database. And our machine runs the background job. When the job runs, it executes the select to process the rows in the table. After processing the rows, it changes the proposal status and does the same for each row in the table, row by row, one by one, until all the rows are processed. Nice? But when you have two machines running our job, we have a distributed background job. Here, both machines run the same application, the same background job, the same code, the same select. And both run the select to process the rows in the table. The first machine processes the first row, and the second machine either. Those machines are processed each row twice, row by row, until there is no more rows to process. Here, depend on what the job does, we can have performance issues or worse, data corruption errors, or both. Oops, we have a race condition here. That's not what I wanted at all. How can I fix that? Maybe a junior developer that doesn't understand very well about distributed systems could suggest to use a synchronized clause. I mean, when I use a synchronized clause in the method, the JVM guarantees for us that the only one thread will execute this method at a time. For example, if you have 10 concurrent threads trying to execute the synchronized method, only one thread will be able to execute it. The others will wait for that chance. So, if you have one single machine, this synchronized solution will work very well. But since you are talking about run the background job in a cluster, we have two or more machines. And each machine will have its own JVM process, which in turn will have its own local lock. And those machines don't talk to each other. No. the synchronized solution does not work for us. Maybe we could use a distributed lock. When I talk about distributed lock, I'm basically talking about having an if statement in the code. Something like that. Here, only the machine, the leader, will be able to execute the job. The other ones, usually called followers or replicas, will wait or sleep. So usually, in order to implement a distributed lock solution, we need a machine in the network to manage all those locks for us. And our machines in the cluster need to communicate to this new machine via low latency network link, so that both machines in the cluster will fight each other to acquire the lock. But only one will acquire the lock. And the machine that acquired the lock will be the leader, so it will execute our job, while the other machine will sleep. And to implement this new machine, we can use an Apache Zookeeper, an Redis, or a MongoDB, for example. But in this talk, we'll not use any one of them. Let's consider that we don't have any of them in our infrastructure. That's why I repeat, look always at the context. But how about using our semi-relational database as a lock provider? I mean, now those machines will try to acquire the lock from the database. In order to implement that, we need to change our Spring Data repository. You just need to annotate the method with lock annotation indicated to Hibernate to use a pessimistic locking strategy. That way, Hibernate will change our select from this to this. Select for update. It means that the select is also locking all the fetched rows from the table. Here we are using a row level lock. Now, when both machines run the select for update statement, they will fight each other to acquire the lock for that row. But only one of them will acquire the lock. The other one will wait. The machine that acquired the lock will process that row. And when it finishes, it will commit the transaction. When it commits the transaction, the lock is released. So the other machine will detect that the lock was released and will reevaluate the select. Since the proposal status changed, that row doesn't match the initial criteria anymore. Then both machines will try to read the next row and fight each other to acquire the lock. But only one will acquire it, while the other one sleeps. The row is processed, the transaction is committed, and the lock is released. The select is reevaluated, and they repeat it again and again. So this is fantastic. We have got not only the ability to remain available in the face of failures, but also we got a safe concurrency control to prevent race conditions and avoid to corrupt data in the database. What if? What if you need more throughput? What if you have a huge table with tens of millions of rows? What if a single machine cannot process all those rows as fast as the business needs? I mean, our current solution allows us to add new machines to the cluster. It does not matter if you have 2 or 3 machines. They will fight each other to acquire the lock. But only one machine will acquire the lock. In that machine will run our job, while the other machine will sleep. And this is terrible because most of the machines in our cluster will be idle. We are wasting computing resource here. That's not what I want. What I want is to have all the machines in the cluster processing our proposal. The idea here is to distribute the workload among all the machines so that we can improve our throughput. To distribute this load, we can use a queue, a message queue. So we have a queue data structure that could store millions of messages and keep their order. And we also could have a process called producer to add messages in the queue. And on the other side, we could have consumers to pick and process all these messages in the same order. And if you need more throughput, we can just add new consumers. This way, those concurrent consumers will pick different messages from the queue and distribute the load between them. When we talk about message queues, what comes into your mind? Probably Kafka, probably RabbitMQ, right? The right tool to solve the right problem. But no, this time we'll not use them. How about using our relational database again? I mean, looking at our context, we could use our database as a queue. And that's not that hard. To do that, we must come back to our repository. Since the repository already uses a pessimistic locking, we just need to add a query hint annotation to indicate Hibernate to use the skip locked feature. So, our select for update will change from that to this. Select for update skip locked. And what does it mean? Let's understand how it works. We have again two machines running our job. They both will execute the same select and will fight each other to acquire a lock. But only one will succeed. The other one will realize the lock was acquired by another transaction, another process, another application. And instead of waiting for the lock, it will skip to the next row. Since the next row is not locked, that machine will also acquire a lock. Then both machines will process different rows concurrently. The first machine commits the transaction and releases the lock. The second machine also finishes and releases its lock. The first machine reads the next row and acquire a new lock. Then the second machine tries to read the same row. But since the row is already locked by the first machine, the second machine escapes this row again. And then it reads and locks the next row. In other words, guys, if you have a table with 4 pending rows and we have 4 machines, that means that each machine will read and lock a different row from each other. They will process each row in parallel. That's exactly what you are looking for. We just got scalability. We have not only improved the throughput of our background job, in addition to that, you can now scale the solution just by adding new consumers, new machines, new processes, new threads. It's the same capability we have when we are using a broker like Kafka or RabbitMQ. And what if we need more performance? What if we need to tune our code in order to use less machines in the cluster? Let's get back to the code again. Here, our business logic. Here's a business logic that runs inside a transaction. It fetches a chunk of 50 proposals. For each proposal, it executes these 2 write operations. One to insert a card and another one to update the proposal. For each iteration in the loop, I mean, for each proposal, Hibernate does 2 round trips. One round trip for the insert and another one for the update. So if you have 2 proposals, we have 4 round trips. If you have 3 proposals, we have 6 round trips. If you have 50 proposals, which is the size of our chunk, we have 100 round trips. It doesn't matter if your SQL statement is too fast. We just hit a very common problem with distributed systems: latency. One way to solve that is using the Hibernate batch size feature. This feature will configure the Hibernate to group similar SQL statements and try to send them in a few round trips. Basically, we need to configure the application YAML with some properties. The first one is the batch size. Here we set it to 50 because it's the size of our chunk of proposal. The other ones are this here: order inserts and order updates. They are responsible for reordering those statements so that Hibernate can group them. Now, for each batch of 50 proposals, not each proposal, each batch of 50 proposals, Hibernate will not do 100 round trips, but only 2. One round trip for insert and another round trip for update. The difference here is that now Hibernate is sent all inserts into a single statement. The same thing to update. So now you just got optional batching processing. Besides getting a better performance in the batching processing, we also did that without changing one single line of Java code, only turning our ORM framework. That is impressive. What if something goes wrong with the network? Here our code again. For each proposal, it makes a remote call to an external system. And every time we have a remote call, we hit the 8 fallacy of distributed system. We live and we die for those 8 lies. I mean, the single line may have a lot of issues, a lot of red flags. What if this method takes too long? 1 minute, 1 hour, infinitely? Of course, we resolve that with timeouts. What if there are transient and temporary errors in the network? Of course, you can solve it with retry and backoff policy. But since you are doing retries, what if the external system cannot receive the same request again? What if it does not implement idempotency? What if you have version problem with the payloads of the external system? What if you have a network partition in our infrastructure? What if a simple remote call like that can present many what ifs? But we are done for now. Concluding, design and implement a background job can be harder than we would like. And depending on the context, the system and business requirements, again, depend on the context. You probably don't need to implement all the solutions that we discussed here. Honestly, depend on your context, you even don't have to implement any one of them. So, finally, to understand everything that we discussed here, let's do a fast recap. Now, we have built a background job that can recover from crash and restart because we embraced the SACD properties of a relational database. We have a background job that can handle a huge volumes of data because it is working in batch. We have a background job that can remain available in the face of failures because it can be run in a cluster. We have a background job that was designed and built to be scalable, thanks to skip locked featuring. And we have a background job that was optimized for high throughput, thanks to Hibernate batch size configuration. And we did all of it using Spring Boot, because we are in a conference about Spring Boot. But it also works on any other platform, .NET, Ruby on Rails, PHP. Because the focus of this talk was not only on Spring, but also on the fundamentals of distributed system and concurrent computing. Okay? I hope you have enjoyed this talk as much as I did preparing it for you guys. Thank you very much.